Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to serve you, as it is every day in my virtual math classroom as I teach you some more goodness of the math world, kind of in algebra realm right now. Pretty soon we'll stick to some geometry, we'll see when that comes up. Today I'm going to be doing an overview and review with some practice problems on solving linear systems. We've been doing things on solving by graphing, substitution, and elimination, and all three will be coming through. There are a couple word problems in this mix, but the models, the equations, the systems, they're already set up for you. So in terms of solving them, we're just answering those bits. And in the next unit that I do, just to let you know, we'll be solving more systems, only those times we'll be using word problems and setting up the equations, and we'll also be solving systems of inequalities. I'll teach you how to graph two variable inequalities at that time as well. But let's start and do this one in a second. I have 16 practice problems for us to do. I think the first 13 are solving systems, and then there are 3 more just review problems. I think solving for x, looking at things that are functions. Should be a pretty briskly paced format here. I'll be solving by the method that they ask me to solve for, unless they allow me to solve freely, in which case I'll solve by the ones that are very viable for me to solve with. If you saw my last 2 videos, I really talked about the pros and cons of solving each method. And then in the very most recent video, I showed you, let's checkbox each method I should solve for and why, so I did more than one. So if I can solve for more than one, and it seems like it's reasonable to, then I will do that. So we'll go and get started. If you kind of see on the TV in the background here, I've had drier eyes before. Definitely, this is the, this marks for me, for my lifetime, and I'm going to try and avoid feeling emotional about it. And he's not my favorite athlete. He's well respected, and I did adore him. But Kobe Bryant had passed today, and his daughter, and 7 other people in a tragic helicopter crash. I don't want to talk too deep about it. I know this is a math channel, but just to let you know that my phone had been going off a lot earlier today, so if you hear vibrations, that's why. I still need to get the alerts that I need to get. If I need to pause the video for a phone call, I will. This is... My heart is very heavy today. So anyway, if there's something, if you don't know who Kobe Bryant is, get out from underneath your rock. If you want to learn and invest more on him, maybe you can see little glimpses in the background with me today. All right, so I'm just, excuse me, already choking up a little. I'm going to stop now. All right, so I'm going to go ahead and get going now. Let's go and start with problem number 1. And in problem numbers 1 and 2, I believe we're going to solve by substitution here. So let's solve by substitution, the substitution method. And what's great is when they ask you to do this, it's likely that the problem is probably well set up for you to solve by substitution already, in which case this problem is. Solve by substitution, y equals 3x minus 2. That's what the equation tells us right here. Y and 3x minus 2 are equivalent. So what I'm going to do is I'm going to take 3x minus 2 in and substitute it for y in the other equation. And what I create in this instance is a single equation with a single variable, in which case I can then solve for that single variable. Okay, so negative 2x plus the quantity 3x minus 2, which is y, equals negative 5. Now, these parentheses actually have no significant bearing or impact on my problem other than to show you that that's what's substituted for y, so I can happily write it without those parentheses as well. Negative 2x plus 3x combine to become positive 1x, and if I add 2 to both sides right here, I'm going to go ahead and get x equals negative 3. So I've now solved for my x variable, but as you've known by solving for systems, I am not yet done with this problem. I have to also solve for y, and then write my final solution as an ordered pair, as it would make sense that I do when I solve by graphing, which we will do today. So to solve for y, I'm going to go ahead and take the top equation right here, because it's already in y equals format. I'm going to rewrite 3x minus 2, but instead of x, use parentheses of course, I will write negative 3, as that is the value for x. Y equals 3 times negative 3 minus 2, which is negative 9 minus 2, and y equals negative 11. As my students are going to be assessed on this material here, and as I'm sure you will as well, be okay with seeing and being comfortable with the idea that you will get some pretty clean answers out for the most part, and that they wouldn't force you to solve by substitution unless it was primed to get to solve by substitution very easily. In other words, if a variable wasn't isolated, I could isolate it very easily, like this bottom equation. I could have added 2x to both sides, and I get y equals 2x plus 5, or minus 5, excuse me. And that could be a very quick way to go from one to the other to do that. No fractions necessary, if you know what I mean. Negative 3, negative 11, excuse me, is my final answer on that. If you wish to double check any of these, and if you have a question as to whether any of these are correct or incorrect, and I won't do this any other time but this one, let's go ahead and substitute negative 3 and negative 11 into both equations and see if we get a true statement out. In the top equation, 3x minus 2, or 3x minus 2 equals y, so 3 times negative 3 minus 2 equals negative 11, negative 9 minus 2 equals negative 11, negative 11 equals negative 11. That one should check out already because that was the very last step that I did here, and it goes to show that it's a solution to that equation. What I need to see is if it's a solution to the other equation as well. I think that's the biggie that I haven't really checked on yet. This one right here, or the rewrite, doesn't matter which one, but I prefer the original. Main reason I prefer the original is because if you made a mistake leading up to that, like if I subtracted 2x from both sides by accident or something like that, suddenly I'm checking in an equation that's not correct. I need to check my original source information and see if I got it correct here. In here, negative 3 times negative 2 plus negative 11 equals negative 5. Let's see how that one pans out. That is a 6, and that's a minus 11 equals negative 5, and 6 minus 11 is negative 5. So negative 5 equals negative 5, it checks out. So once again, you can check and see if your information is correct, assuming that you do your double check calculations properly. Why is Wolf Blitzer on? This is NBA TV. This is weird. Assuming that, what was I saying? Assuming that you do your math correctly and your double check stuff and left equals right, then you can feel good about your answer there and you can move on. You don't have to ask somebody else or check with a calculator or anything like that, to see that. That being said, if you're incorrect, if you don't get the left to equal the right on both sides here, when you're doing, say I get negative 11 equals negative 13 or something random, it's harder to dissect where your problem is. So double checking is good if you're right, and it's good if you're wrong if you want to correct something, but it doesn't tell you where you're incorrect. I want to make sure you know that. You got to go back in your work and go like, oops, I did 3 times negative 3 and I put positive 9. You know, something like that. Something like that happened there. All right, that's it for number 1. The next problems will be significantly faster because I won't double check, and now that I've done substitution, I'll do it again. Solve by substitution number 2, y equals this, y equals that. You know, what's really great about this kind of problem here is that I can just substitute this in for this y right here, and I'm already set. No distribution necessary. Very clean problem to do here. Negative 2x minus 5 is going to take place of that leftmost y, and that's going to equal that right expression, 2x minus 1. And that's the way that I would ideally do this problem. That's substitution. Let's take care of the rest. I'm going to add 2x to both sides here, all right? And I'm going to go ahead and add 1 to both sides. So I'm moving my constants on the left and the variables on the right. I don't know why I crossed that out. That's not allowed. Some people will move the x's on the left. I just like to keep my x terms positive. If you watched my channel before, you have probably heard that statement before. Divide both sides by 4. I'm going to get x equals negative 1. If you need to see that step, I'll go ahead and write it. Divide by 4, divide by 4. And then, of course, I just wrote the x term on this side and the negative 1 on that side. X equals negative 1. I'm not finished with this problem, though, of course. I'll box it just to make sure I see it true. I'm going to take this bottom equation, and I'm going to substitute. Y equals 2 times negative 1 minus 1. That's my solution for x. That's y equals negative 2 minus 1, or y equals negative 3. So my final solution statement right there is negative 1, comma, negative 3. Again, I'm not going to double check this one. Feel free to do so as necessary for your own sake of practice. I'm going to trust I did the right answer there. I'm prone to making mistakes. I almost canceled out of negative 5 and a 1 for crying out loud. But I'm going to trust that that's true and that works out, and I'm going to happily move on from there. All right, number 3, I'm going to solve by graphing. And if I recall correctly, when I set this thing up, number 6 is also solving by graphing, so there's a jump. So if you want to see 2 graphing ones in a row, go from number 3 then to number 6. 4 and 5, I think, are on elimination, just so you're aware. Number 3, solve by graphing. Negative 3x plus y equals 2, y equals negative 2x minus 8. All right. As this one's asking me to solve by graphing here, slope-intercept form like this one, y equals mx plus b, is very ideal to graph in. So I'm going to go ahead and start with this one just first. So negative 2x minus 8, negative 8 is my y-intercept. My slope is negative 2 over 1, which means I fall 2 and run 1 to find a brand new point like that one there. And I can rise 2 and run 1 to the left to find other points right here of significance. When I plot all these points on the graph, and you can go as far as you need to, but if you don't have a ruler or need to make the straightest line possible, go ahead and get as many points as you can fit and then use your ruler or not and graph the line. So make sure you use arrows as well. Of course, we're just finding the point of intersection. It's one thing to graph these lines and be accurate with it and make sure you're doing all that you're asked to, but it's another one to say that we are just finding the point of intersection. So I really could have probably stopped at some point prior to. Now I want to graph the green one now here as well, but you know, this is written in standard form, which isn't bad to graph when it comes to finding intercepts. Like for instance, I already know the y-intercept right now is 2, using my good old hide and divide method right there. Don't even have to divide, y equals 2, so I know that's a point on this graph. However, my x-intercept would have been, if I hide and divide, I get x equals negative 2/3. And, you know, being a fraction, I don't like the idea of this point very proper. Like, I can't know for myself that this is essentially negative 2/3 very well. And by extrapolating that and drawing a huge line based on it, I can't guarantee that my line will be perfect with accuracy. So I'm not going to stick just with doing the x and y intercept here. I'm going to go into slope-intercept form for myself on this problem. And in doing so, I'm going to add 3x to both sides. Plus 3x plus 3x. I get the equation y equals 3x plus 2. I think this is a lot better off when it comes to me being accurate. I do have the y-intercept of 2. That was a good start. And I can rise 3 and run 1 to find another point, as my slope is positive 3. Now in going downwards, because this is the important stage right here, I have to find out where this intersects with the blue line. I'm going to go down 3 and over 1 here, and that's a much better point to go off of to know this will connect. And I'm going to continue down 3, left 1, down 3, left 1. You can already see where I found the point of intersection. I will get to that as soon as I connect the dots on this graph here. So get a little arrow. All right, and let's connect that up. And my point of intersection is the thing that we were trying to solve by graphing. We want to find out where these 2 points intersect, which is right here. And I don't want to make a mistake. This is negative 2 for x, and this is, I believe, negative 4 for y. Again, I don't want to make the mistake. I believe that's correct. Make sure that you write the correct point, but you have to write the point in general. You don't just let them intersect and let it be. Do that last step, just like I did for solving by substitution. Negative 2, negative 4. Sounds good. All right. Number 4 and 5, like I said, are solved by elimination, and then I go solve by graphing again in number 6. Kind of different story. All right, number 4 is solved by elimination here. X minus 2y equals negative 7. 4x plus 2y equals 22. Both equations are written in standard form, and that is best for solving by elimination. Currently, and I'm not going to explain why I can do it right now. I have video concerning that, but you can add down these columns as long as like terms can combine and they're aligned with the equal sign. I can add straight down these lists as I'd like to, and I will. Negative 2y plus 2y equals 0. Those two will cancel out, or better yet, use the word eliminate. Those two will eliminate the y variable, and I'll be left with just an x variable in my equation, where I only have x plus 4x equaling 5x. Equals negative 7 plus 22. 22 minus 7 is 15. 5x equals 15. Divide by 5, you get x equals 3. A lot of people are like, oh, golly gee, I like substitution a lot. You know what? So do I. Or excuse me, elimination. So do I. I do. Of course, this was also very set up for it, but it's a very clean method. It does help to know why you can do this, but as long as you know the process, that's good too. I'm not done. I have to still solve for y. I'm going to use the bottom equation. If you can tell what equations I tend to use, either I use equations with smaller numbers, which this one's not the case, or the ones with more positives when I am able to, which in this case was the case. Substitute 3 for x. 4 times 3 is 12. 12 plus 2y equals 22. Subtract 12 from both sides. I'm going to get 2y equals 10. Divide both sides by 2. I'm going to get y equals 5. So I have an ordered pair of 3, 5 as my solution set. That is not the only way to solve the problem, but that is indeed the fastest way. I could have eliminated x by doing some things here. I'll likely have to do something like that in the next problem. So let's take a look at it. Number 5, solved by elimination. Yes, there it is. 4x minus 2y equals 2. 2x plus y equals negative 5. If I add down these lists at this very moment, which I will write in red for not for incorrectness, but for lack of productivity. Actually, I take it back. There's something I could do with it. I would get 6x minus y equals, there's a text. 6x minus y, yeah, equals negative 3. Hold on one second here. stopping math for a text. This is an immediate text thing I got to do. It's about Kobe. Okay, I get 6x minus y equals negative 3. Adding down the list didn't immediately help me because I didn't have additive inverse coefficients in this particular problem to cancel out a variable. The whole goal, like this last problem here, is to get a variable by itself in one equation. The y's went away, I'm left with x I can solve. Here, neither y nor x went away in this equation. I can't solve there. I'll let you know what though. This equation is a solution to your system, the x and y that I get here is a solution to the system will find the same point of intersection all of these on a graph. If I graphed all three of these, they would all intersect at the same point. Even though I made a new equation based off this information, this would. So I could use this equation. I could merge it with the bottom equation right here, and I can cancel out the y's right there, and I can solve this thing. And you can practice that right now, and you can, but it's unlikely for you guys to have discovered that, and I didn't discover it except for by pure happenstance that would happen. Most people aren't going to do the problem this way, but you could. Y minus y is 0, boom, goes away, solve for x. Looks like we're going to get negative 1 for x. I'm going to do it a more, not natural way, well, more natural in the sense that it's something you would naturally do. So let's go ahead and find an alternative approach here. I'm going to cancel either y or x by manipulating just one of these equations, because it looks like if I multiply y by 2, and I'll get 2y, the y's can cancel out here. If I multiply x by 2, or 2x by 2, I'll get 4x, and that should help line this up as well. Or I could divide this one by, you know what? I could divide this one by 2 as well. I didn't see that before. You have a lot of options here. I'm going to choose to, just from what I think most people are going to see first, I want to follow that. I'm going to cancel out the y's here, not by dividing the top by 2, which is very recommended for those who know how to do it, but I'm going to multiply the bottom by 2. I think that's what most people would see first. That's what I saw first, so I'm just going to jump to that. If I multiply that by 2, I'm going to get 4x plus 2y equals negative 10. Now, why did I choose y and not x? Because this is negative, this is positive already. They're set to cancel. I didn't have to multiply by a negative value, because on x I'd have to multiply top and bottom by negative 2. All right, I'm going to hide that away so you can see top and bottom right here. 4x and 4x are going to add to become 8x. Oops, I wanted black. Are going to add to become 8x here. Negative 2y plus 2y go away. They eliminate. Equals 2 minus 10, that's negative 8. And x equals negative 1. And as I clearly love to listen to myself talk, that problem could have been solved a lot faster. But I want you to see the ins and outs. If you're watching this video, hopefully you're not just looking for an answer. Download PhotoMath, take a picture of this thing, and look at the answer there if you'd really like to see it. Or go to desmos.com, graph these two, find the point of intersection. I want you to explore the options in this problem. Yes, I'm only doing it one way, but you heard me talk about other approaches you can do as well. All right, solve for y. I'm going to go to this original equation that I kind of canceled out here. Substitute the negative 1 in for x there. Because, you know, the whole point is that, I'm going back to the whole, why am I taking a long time to talk about this thing? You want to have an inner voice when you're doing these problems. I'm going to add 2 to both sides, by the way. You want to have an inner voice when you're doing these problems. If you're being assessed and you can't say anything out loud, you want to have some voice talking to you. If it's yourself, if it's me, if it's whatever it is, or a picture in your head, I want you to have that. And then ask yourself here, what would Mr. Robinson do? No, just ask yourself, what would be most efficient, most logical, what's accepted? Those are the kinds of questions you need to ask, because here's the thing. There's more than one way to solve this problem. But if you're being forced by elimination, what's the best variable to cancel? What options have I tried? You know, things like that. Anyway, final answer for this one's negative 1, negative 3. Let's move on. Number 6, solve by graphing. Like I said, this would pop up again. This is a good time for me to solve using the standard form, finding the intercepts, as I didn't last time. I used only slope-intercept form. But in this particular problem here, everything's going to clean up very nicely for me, where I can get my intercepts very nicely. Let's start with the top one right here. To find the x-intercept, I'm going to go ahead and hide the y, and then divide. Hide. Now, why am I hiding, in case you don't know? I'm setting y equal to 0. The x-intercept is something, comma 0. I'm setting y equal to 0. 3 times 0 is 0, and it goes away. So I hide it. Hide. 3x equals 15. Divide by 3, you get x equals 5. That's why I'm calling it hide and divide. Excuse me, the y-intercept, we set x equal to 0, so same thing, hide. Oh, that carried with it, sorry about that. Let's ungroup that. There we go. We hide, and then divide. It looks like the y-intercept is 5 as well. That's 0, 5. You don't have to put the coordinate pairs like that, but I was overexpressing the fact that the other is 0. That's why I hide. Also, you don't want to put them in the wrong spot. Thankfully, they're both a 5. So 5 for the x-intercept, 5 for the y-intercept. And as I generally say here, 2 points make a line, so I can happily draw the line here. You really would want a ruler for this scenario here, because it's likely that your point of intersection on this blue with my next one that's going to be green will not be on just the x or y intercept. It's possible, but it's, the odds are not in your favor for that. So you want to make sure it's going through the right points. If you can tell, though, the slope is -1, down 1 over 1. And it looks like this one's going to have something in terms of a 1 slope as well, because I'm looking at same coefficients of 1, +1, -1. But let's go ahead and get that x and y intercept here. In the same case, hide and divide. X-intercept, 0 for y, hide y. Nothing to divide, x equals 3. That is my x-intercept right here, 3. Hide and divide here for y. Make sure you only hide the x and not the negative here. When negative y is +3, that would mean that positive y is -3. When I set x equal to 0, y is -3. So I go ahead and plot that point as well. And 2 points make a line, of course. One more time, let's go ahead and craft that. Looks like it's going to go straight down through that slot right there. If I did it correctly, I think I did. And the whole point is to find the point. The whole point is to find the point of intersection that is right here where these two things cross. And it looks like we're going to get 4, 1. That is my solution set for that one. You can double check by substituting things back into the original equations if you ever so choose to right there. That's my solve by graphing. Number 7, solve using any method of your choosing. I have a graph up here because I'm going to use all 3 methods. Let's start with the graphing method, actually, just because we came off the heels of that one. So I'm trying to pick colors here. Graphing, I'll go ahead and use blue. So in solving by graphing, I can do the same thing as I did before in terms of hide and divide, yada yada. So let's do that for the bottom one, because the top one here, if I divide by 4, I get a fraction x-intercept. That's a problem. So for the top equation, I'm going to write y equals -4x minus 1. I subtracted 4x from both sides, and that's what I got. So let's go down, start at -1 for the y-intercept. Let's go down 4 over 1, down 4 over 1, etc. Let's draw that line. I'm going to do this entirely in blue for graphing. Hope you're okay with that, because I'm going to use other colors for the other problems just so you know what I'm setting up there. So there's that graph right there. And then I also, of course, need to graph the bottom equation here. If I use the old hide and divide method, and of course I could use slope-intercept form, but why not combine them? Negative x is +4, so x equals -4. So -4, 0 is 1 point. For the y-intercept, for this guy right here, y equals 4. Oh, one of those things again. Sometimes that software does not want to play with you very friendly. There we go. Y equals 4, so that's 0, 4, and that is that point right here. Of course, 2 points make a line. I'm going to go ahead and get close enough and graph that. All right, point of intersection looks to be, and you know what? That's not the prettiest scaling for me. It's not the prettiest graph. I assume it's hitting that integer. There we go, right there. Looks like this is going to be the point, whoop, right there. That is, I think, -1, 3. That is the final solution to that one there. I'll confirm that, not by double checking by plugging things in here, but I'll confirm it by using the other 2 methods. I'm going to use substitution method and elimination method for the next 2. Okay, let's go and use substitution method next. That's going to be the big S. That's not a 5. Hopefully you can tell. Through substitution method, let's go ahead and isolate y in one of the equations. I think because they're both positive y's, that would be best. I already isolated y in this one, but because it's negatives, let's just go ahead and do the bottom one. Y equals x plus 4. If I add x to both sides, y equals x plus 4. That is rewriting that equation there. Now I'm going to take the top equation, and I'm going to substitute y in for, x plus 4 in for y in that top part right there. All right, 4x plus y equals -1. And the parentheses were not important in this stage right here, so I can remove them. 4x plus x is 5x. If I subtract 4 from both sides, I'm going to get negative 5 on this side. We get x equals negative 1, which aptly fits the previous problem that I did there. Excuse me. Now let's solve for y here. Let's go ahead and put it in that equation right there. Y equals negative 1 plus 4, negative 1 for x, and y equals positive 3. So once again, I get the solution set negative 1 comma 3 using substitution. Very nice method to be choosing right there. Okay. And the last scenario that I'm going to do here is using the elimination method. And in the elimination method, I'll just do this in one fell swoop. I'm going to multiply the bottom equation here by negative 1. I'm going to multiply by negative 1 because I can then cancel out these y's. I could multiply the bottom equation by 4, for example, and cancel out the x's, but bigger numbers maybe don't want to prevail a different way here. So I'm going to rewrite both equations though. 4x plus y equals negative 1. And this time, negative 1 times negative x is a positive x, minus y equals negative 4. In canceling out these y's here, as they'll go away, I'm going to go ahead and get 5x equals negative 5. Divide both sides by 5, I get x equals negative 1. And of course, go ahead and substitute. Let's try the top equation this time because I haven't played with that one through substitution yet. 4 times negative 1 plus y equals negative 1. And negative 4 plus y equals negative 1, and y equals 3. You might have wondered why I did not go ahead, and I'm going to box right here. You might have wondered why I did not go ahead and substitute x into the equation that says y equals x plus 4. Well, 1, we already did that. And 2, I'm playing with the elimination method as if I didn't use this method yet. So yes, I could rewrite this equation for myself again, but it's likely you're going to go back to one of your original standard form equations when you do that. All right, negative 1 comma 3 is the interlinking solution to this problem, no matter which method I chose there. And I am set to go. All right, number 8. Here is one of those word problems I was talking about. In this one, there is a little bit of something that I do want to talk about with the model because you have decimals. And I don't think I've played with those once yet with you guys. So let's do this. Shantae has 21 coins, all of them nickels. All damn nickels. Oh, all of the coins are nickels. I'm just reading out like all damn nickels and dimes. Shantae has 21 coins, all of them being nickels and dimes, that are worth $1.70. The following system of equations describes the situation. And I'm going to do a couple of rewrites for this thing because I want you to play with what this says. When we set up word problems in the next unit, I want you to know why this says what it does. But here is the situation. X plus y equals 21, 0.05x plus 0.1y equals 1.7. Solve the system, show your work. How many nickels and how many dimes does Shantae have? Okay. Couple things here. Let's talk about how this equation was kind of set up. And furthermore, I mean, look, what you're going to do is you're going to solve for x and y. I want to make sure you know that from the onset. We are solving x and y. Okay. But here's the thing. What is x and what is y? Which one represents which? If I only have this equation, x plus y equals 21, it's completely valid. One of them could be nickels, one of them could be dimes, and you could interchange them, and there's no bother. But then you see this one down here, and you see a 0.05x and a 0.1y, and what do these have to do with? Well, let's go ahead and kind of rewrite this whole thing. I'm just going to rewrite the top one as is, x plus y equals 21. I'm going to kind of keep them in a nice line here. And in the bottom one, I'm going to rewrite this, but I'm going to do something very minorly different. And I'm going to change these so they all have 2 decimal places. Instead of 0.1y, I'm going to write 0.10y. And this 1.7, I'm going to write 1.70. Why does this help me? Because of how we look at money. We as in US dollars and how the decimal portion for cents work. We see 2 decimal places to represent those cents. This clearly shows it for the 0.05. If you see something on a cash register that says 0.05, to you that should mean $0.05, which is 5 cents. And if this is 5 cents here, I'll let you know what this talks about. 5 cents is attached to a nickel. So X must represent number of nickels. And I say number of because if you look at the top equation, here, you are looking at number of nickels plus, and assuming this will be number of dimes, equals number of coins in total, right? This is the number of coins that you have. So they all have to be the same thing. Number of coins plus number of coins equals number of coins. This is not the value of a nickel. We know the value of a nickel, and the value is going to be attached in the second equation. X is number of nickels, Y is number of dimes. And we can see that a little better now that we change 0.1 to 0.10. 10 cents. 10 cents per dime. And here's really where the kicker is, the $1.70. This guy right here told us the 1.70. That's what this whole equation's about, value. 0.05x is $0.05 times x. Excuse me, yeah, $0.05, it is dollars, times x coins, times x nickels, equals the value in dollars of all the nickels that you have. Let's put it this way, and I don't know the answer. If the answer was 4, if I had 4 nickels, I'd do 0.05 times 4. 0.05 times 4 equals 0.20, which is 20 cents. That is the value of my 4 nickels that I have. So that's what this equation is representing. The value of my nickels, all nickels that I have, plus the value of all dimes that I have equals the value of all my coins in dollars here. Okay, that's how this thing's set up here, and I think that's going to be more pertinent to the next unit. But I do want to make sure that you can set this up in a way that's valuable to you. Here's the other thing I want to do with this, because the point for me is to solve this equation. I don't want to use decimals any more than you do. I don't. I'm going to not use decimals. There are 2 ways I can do it, 3 ways. All 3 of them are the same exact thing. And you might want to kind of know all these in every instance. Number 1, you're allowed to do decimal shifts anywhere you'd like to, as long as you do the same amount for every term. I can shift this decimal 2 places to the right to create 5x, as long as I shift this decimal 2 places to the right to create 10y, and shift this decimal 2 places to the right to create 170. Okay? That is option number 1. Now, like I said, I'm going to get to the same place no matter what I do here. It's option number 1. Option number 2, I can multiply everything by 100. Now, how did I know to multiply by 100? Because multiplying by powers of 10 creates decimal shifts. And multiplying by 2 powers of 10, meaning 10 squared, which is 100, multiplying by 2 powers of 10 shifts the decimal 2 places over. 0.05 times 100 is 5x. 0.1, doesn't matter if it's 0.1 or 0.10, times y equals 10, y, and then 1.70 times 100 equals 170. It's the same thing. Option number 3, and this is kind of not using as much math as it is understanding currency. Remember what I said here about this whole thing being measured in dollars. These are in dollars right now. $1.70 is $1.70, $0.05 is 5 cents, things like that. What if we rewrite it as cents? We don't use dollar values. What if we use cent values? We don't call this $1.70. What if we said 170 cents? That's how much is $1.70. It's 170 pennies. So what if I do that? Instead of writing $0.05 per nickel, I can say 5 cents per nickel times x plus 10 cents per dime times the number of dimes equals 170 cents. So if you have an equation that you want to, or if you have a word problem that you want to create an equation in a system and you want to use some certain value, it's written in dollars to start off, and albeit not using all the insignificant decimals, those zeros, and you can just convert it to cents on the fly. That's up to you. That's all in cents. This is the same equation all 3 times. Now, it might sound like to you that I'm over-speaking this problem, but I promise you I'm not. If you didn't know how to do either of these first 2 when it comes to these things, you should want to know how to represent the dollars to cents conversion by understanding that you can represent this in more than one way if you so choose to, because like you, I don't want to use decimals. Now, all 3 of these things are the same exact equation, so what I'm going to do, I'm going to solve the system down here, I'm going to show my work, and I'm going to rewrite this. I'm going to have, let's go ahead. I'm going to, because I don't have much room, because my face, of course, is in the way. I'm going to erase some of these things. I'm going to rewrite the 5x thing, but right underneath here we go. We're going to get 5x, let's fix that y here first. We're going to get 5x plus 10y equals 170. Brilliant system, go ahead and solve for that thing. Now I have a bunch of options here. Before I talk about multiplication, I want to do division this time. All of these numbers are divisible by 5. Maybe you know that, maybe you don't. But all these numbers, they're big enough as is, they're all divisible by 5. They end in 5 or 0. So I'm going to divide everything by 5, but not actually just 5. I'm going to divide by negative 5. If I divide everything by negative 5 here, I'm going to get that thing to now say, if I rewrite the top one, x plus y equals 21, the bottom one will now say negative x minus 2y equals negative, oh, well, now that's a problem. Do that with me, 34. I think negative 34. All right. Now you might, if you have a calculator, that's more power to you. Why did I divide by negative 5? Because I can cancel out these x's right here. All right, I'm finding the thing I can cancel out and divide here. And I didn't divide by negative 10 because 5 doesn't divide by 10 without having a fraction. Y minus 2y is negative y. 21 minus 34 is negative 13. Negative y equals negative 13, so y equals positive 13. All right, let's use that to solve for x. Let's use that top equation there, x plus y equals 21. X plus 13 equals 21, subtract 13, x equals 8. Okay, how many nickels and how many dimes does Shante have? Now, by the way, solve the system. If I write it as an ordered pair, cool, but I'll let you know an ordered pair doesn't mean too much for us unless we graph it. Because this is a word problem. X represents something, Y represents something. And that's what the second question's asking. How many nickels and how many dimes does Shante have? And Shante, let's type this one out. Shante has 8 nickels because X is number of nickels, and 13 dimes. Hold on. How do you spell it? Shante has, of course it's misspelled, has 8 nickels and 13 dimes. Now let's double check that. Let's see if that actually works out through everything, because we understand how money works. So I think we're more likely to want to, we can double check this one without thinking about the math too much here. 8 nickels and 13 dimes is 21 coins total. The top equation works. Is this $1.70? 13 dimes is $1.30. 8 nickels, that's 5 cents each, is 40 cents total. $1.30 plus 40 cents is $1.70. So that one does seem to work out there. Okay. Hang on 1 second. Okay, I'm good. Okay, so I'll set there. So in solving that, keep in mind it was good to get the decimal portion fixed. There were 3 remedies, which I showed you for this particular word problem. Because I converted from dollars to cents, it actually worked out even better for me in that instance. All right, number 9, the hare has challenged the tortoise to another race. The hare offers the tortoise a 435-meter head start. It's generous. The race path is 500 meters long, and the tortoise moves at a rate of 5 meters per minute. The hare knows that he moves at a rate 30 times faster than the tortoise. Now, good news for you, again, this information is just telling it to you. There's a model right here. The following functions, g of t and h of t, represent the distance d in meters the tortoise and the hare respectively have traveled t minutes after the hare begins running. Now, you don't see a variable d right here. It's being replaced by g of t and h of t. D is g of t, d is h of t. What they're saying is, based on a certain time, I'm going to get a certain distance. But we use 2 separate things here, which isn't needed unless you don't know which one's which. G of t represents the tortoise's distance based on a certain amount of time. What was it, minutes? And the h of t represents the hare, as h aptly stands for hare, and g stands for tortoise somehow. But the distance covered is based on, if I substitute 1 for t, I get an answer that's distance in what, meters? In meters. Okay. Now there's a parts A and B. My face is kind of covering B right here, but parts A and B right here. And I'll just do A right now. I'll stick in the slide for now. Complete the table for the 2 functions. We'll substitute these values in for t, and then we'll get values out for g of t, or h of t, or d, of course. G of 0 equals 5 times 0 plus 435. I'm not going to show the work each time. You're going to get it after some point. That's 0 plus 435, which is, 435. So after 0 minutes, when the race begins, the tortoise starts out 435 meters ahead. That kind of represents what the problem tells you. H equals 1, ht equals 150t. Actually, before I keep moving on, I want to just talk about how these equations were made. 435 meter head start is this portion right here, and we just noticed that after 0 minutes, the tortoise has covered 435 meters. And he's going to cover then 5 meters per minute, the tortoise is, and that's what that's what's happening here. 5 meters per minute times the number of minutes. If he goes for 10 minutes, that's an extra 50 meters, things like that. That one makes more sense. Where does 150t come from? I don't see the number 150 anywhere here. anywhere. I see the number 500, that's not used anywhere. I see a 30, that's not used anywhere. Where does 150 come from? There's a comparison that's happening between the tortoise and the hare, and it's spoken of right here, 30 times faster. The hare is 30 times faster than the tortoise. The hare, I'm not going to use T's here, but the hare is 30 times faster than the, let's just use G, than the tortoise. Whatever the tortoise's speed is, this is G in terms of speed, the tortoise is 5 meters per minute. So 30 times 5 is 150. That is the meters per minute. That is the rate of the hare. Hare travels 150 meters per minute. That's where you're getting the 150t. Now, there's no y-intercept because the hare starts at the starting line, so to speak, whereas the tortoise is way ahead at 435. That's where we're getting that information. So when we do h of 0 equals 150 times 0, after 0 minutes, the hare is 0 meters into the race because the race technically just started or hasn't started or what have you. This is where they are to start with. After we substitute 1 for each of these, for the tortoise, 5 times 1 plus 435 is 440. Let's continue with the tortoise here. 5 times 2 is 10 plus 435 is 445. And you might notice 435, 440, 445. We're going up by 5 every minute, and that makes sense for the context of the problem. Add 5 again, 450. Add 5 again, 455. That's a nice concept of linear functions. They stay at a constant rate as long as these go up at a constant rate. And you can apply the same thing right here for this, but as you add, you might as well multiply as well. 150 times 1 is 150. 150 times 2 is 300. 150 or plus 150, if you want to say it that way now, is 450, and then plus 150 again is 600. Okay, so we get those values right there. At some point, it looks like they crossed. In fact, they're going to ask those questions in a second. Does the hare pass the tortoise before the race is over? If so, when and how far have they both run at that time? Answer using the table from part A. I almost wish I had a graph for this problem because then we could interpret and look at the graph and say, with respect to time, who has traveled more, who has covered more distance. And whoever covered more distance at the finish line, therefore, is the winner. You have to understand that they are traveling the same rate. They both started at the same time. So we can see there is this one mark at t equals 3 at the 3rd minute. The 450 meter mark and the 3 minute mark where they are at the same, they're tied. Now they're tied and the hare is running faster. So at the 3 minute mark, they're tied. The hare is going to run faster. So at 3 minutes and 1 second, the hare is now ahead. And the tortoise is like, oh, darn, right? And gets beat. But did it get beat? When did the race end? At 450 meters, have they finished the race? This is where the 500 comes in. 500 meters long is the distance of the thing. So it's 500 meters long. At 450, they haven't finished the race yet. They have 50 more meters to go. Clearly, the hare is going to surpass the tortoise and win this race. So it looks like the hare didn't give the tortoise enough of a head start, or the tortoise was a little too cocky. So does the hare pass the tortoise before the race is over? Yes. If so, and normally you should write more words than I will. If so, when and how far have they both run at the same time? We said at 3 minutes, I'll say tied at 450 meters. Together, they're tied right at that spot. Answer using the table. Okay, we've done that. So that's when they're tied, but yes, the hare wins. Okay, hare past the tortoise, yes. Okay, there's that word problem. Okay, number 10, determine the number of solutions for each system of equations. I have parts A through E. I really do like this problem. It shows different formats of these things, and we have to determine what's the solution set. The graphs will be the easier ones because we know that if they intersect once, it's a single solution. If they are parallel, it's no solution. If they are right on top of each other, it's an infinite number of solutions. In equation form, we can kind of determine it as well based on what we see here. These are two parallel lines here. They will not intersect, therefore they do have 0 solutions. That is A. By the way, you can't have 0 and 1 at the same time. It's only one of these options for each. Part B, y equals 2x plus 4, y equals 2x minus 5. Without graphing, we have to understand that in slope-intercept form, what this represents This is the slope. This is the slope. They have the same slope. Does that mean they're parallel? Parallel does mean non-intersecting, and that can only occur when you do have same slope of two different lines, but they can't be the same line either, meaning they cannot be one on top of another. We can determine that information based off the y-intercepts here. As long as these numbers are different, and I want to say without graphing, but as long as these numbers are different, they will be in different spots, which means they indeed are parallel. In fact, this problem might be the same as this one up here. I don't know, I didn't make these. So we do have 0 solutions on that one. In fact, I got to remind myself right here in a sec, I am going to have to pause the video in 1 second because this was made by another colleague of mine, and he did say that there was a problem that needs to be corrected because there's no correct answer in the multiple choice section. So I think the whole problem is rewritten. It might be one of the next problems coming up. So I am going to pause the video when we run into that problem. I want to let you know that right now, and then I'll come back. Okay, 0 solutions on that one. The next one here, I'll let you know right now, these slopes are different. If the slopes are different and if the lines go forever, that means that eventually one is going to touch the other at some point. Whether negative or positive on x or y, they will intersect somewhere, and they will intersect only once. Okay, this is a 1 solution case. All I need to see is that the slopes are different, and then I'm good. All right. Part D, these intersect only once as well. You have to remember, these are linear systems. Lines, they do go on forever, but they also don't bend or curve or angle. So they'll intersect only once here. They'll never see each other again. Like if the tortoise and hare raced forever, they'd only meet at that 3-minute mark, and the tortoise is going to, eat my dust, bunny or turtle. You know what I mean? Tortoise. This intersects at one point. It's 1 solution. In the last one here, I think the indicator is that thinner, longer line right there, not longer, they're infinite, but the longer drawn line is a single line. The solid, shorter looking representation of the line is another one. One line is right on top of another, and they're intersecting everywhere together, right here and right here and right here, and everywhere that you can see. This is one of those infinite number of solution sets. What does infinitely many solutions look like in equation form? What it looks like is, hold on, just hit a wrong button. What they look like are same slope and same y-intercept. Now you might have equations that are written in standard form as well, and I want to let you know that you might not have the slope and y-intercept there looking at you right in the face when you're in standard form. So you have to rewrite them in y equals mx plus b form or graph them to know whether they have 1 or infinitely many solutions, or you can solve them, of course. You can solve using substitution, elimination, something like that. But just looking right on the onset, I would rather go into slope-intercept form and determine, do they have the same slope? If yes, you got to ask yourself, do they have the same y-intercept? If that's yes, infinitely many solutions. Do they have the same slope? If yes, do they have different y-intercepts? That's no solution. They're parallel. Do they have the same slope? If no, that's 1 solution. They'll only hit at 1 place. Okay. Looks like this is not that problem that's going to be a problem. Let me actually make myself a little smaller. Okay, Julio wants to solve the system shown using the elimination method, which is the best way to begin. Let's look at all 4 options here and see what kind of makes sense and what brings what to what. If I did say A, add the equations, what would happen? By adding the equations, I create negative 3x minus 5y equals 14. Did this help further or help progress my ability to solve this problem? I'm going to argue no. I didn't eliminate a variable. I didn't get a variable isolated, a single positive, negative, positive y, positive x. This did not help. I'm going to say that it is no to A. B, multiply each term in x minus 12y equals 2 by negative 4 and add it to the original equation. That means to the other original equation, negative 4. That means this will become negative 4x plus 48y equals negative 8. When I add these, I get negative 8x plus 55y equals 4. It looked like it did something that was close to good, but not quite. They did not eliminate the x's here. I would still say no, this is not beneficial for the same reason as A. In fact, I took one more step to generate even bigger numbers. That might have been even worse, although it did get me closer to what I think I want to do. C, the system of equations has no solution, so Julio should not do anything. This is hard to talk about whether it's right or wrong right now, because to do this, you'd have to solve it, or do what I said in the last one, rewrite both these in slope-intercept form and see if they have the same slope and different y-intercepts. I'm not going to bother with rewriting right now with all the fraction business right here. Let's skip C for now. Let's talk about D and see if this can help bring us to that talk and what it looks like when you do have no solution, if that actually occurs. So D, let's try this option. Multiply each term in x minus 12y equals 2 by 4 and add it to the original equation. So this one actually might pan out better because now I have a positive 4x, which looks like I can actually cancel my x's here. Looks like D is a pretty viable option right now. But we'll talk a little bit more about part C as well. Minus 48y equals 8. And then when I cancel, I'm going to get negative 41y equals 20. Now I'm not going to solve the rest of this system, but I'll let you know that right now there is an answer to y. It's negative 20 over 41. That is not a very good looking answer. I'm going to let you know right now. But that is an answer. That is a value for y. That is the intersecting point. And then I substitute that into an equation to solve for x, or I find a way to eliminate the y's to solve for x. So the answer is D. The best first step to begin by eliminating is to create additive inverses. Find a way to multiply here. And you notice that they had us eliminate x and not y because it's a lot faster. I have to find a least common multiple of 7 and 12, which is 84. So I'd have to multiply this by 12 and this by 7. It's just going to lead to large numbers. And you know what? I might do that to solve for x if I wanted to, because this is a fraction, and I don't want to substitute in a fraction for this guy here. But D is the correct answer here. Now let's say you still weren't certain on C here, and you said maybe the answer is C. Let me tell you two things about C that we know that this isn't correct. Number one, the fact that I eliminated x's and didn't eliminate y's means there will be a solution. I just mentioned that. Because there's a y equals, there is a solution to this problem. If the y is eliminated, if somehow this turned into negative 7y, say, negative 7y, and they both canceled, and we get 0 equals 20, all right, well, now you have a valid case for C. Now you're saying, oh, guys, this actually is no solution. 0 doesn't equal 20. My variable's canceled. We're good. That didn't happen here. But here's the thing. Even if we had 0 equals 20, and we said no solution and all that, I still don't like C's answer because of this. Julio should not do anything. You gotta determine that it's no solution first to make this thing to happen. So Julio has to do something to show that it's no solution first. Going to 0 equals 20 should make that happen. So Julio should not do anything is not really a measure, unless these are already in slope-intercept form and you get that kind of equation like we saw before, y equals 2x plus 7, y equals 2x minus 1. You get something like this. Okay, I know there's no solution now. Yeah, I'm not gonna do anything now. I understand that. In this problem here, we can't not do anything even if it was no solution, but there is a solution. So it's clearly not C, it is D. Looks like they wanted you to test all these first to figure that out, and that is number 11. Okay, here's number 12. Okay, I think number 12 is the one where there's a mistake. I don't know if they changed it in the email. So I'm going to go ahead. I'm going to pause this video for now. Don't look at this problem in great detail just yet. I'm going to pause this video. When you see it, I'm going to have a rewrite of this equation right here. Hang tight for just 2 seconds. It's 2 seconds for you, about 5 minutes for me. All right, and we're back. You missed me? Okay. All right, so I just rewrote this right here. Here's what he said in the email. This is what we should rewrite it to. I believe the answer he said still sticks up here. I have to hide myself in a second so you can actually see all these. But the point is, I want to kind of find ways to show how to graph this, how to get the graphs for this one correctly first anyway. I'm going to go to slope-intercept form for both of these equations here. Add x to both sides, I get y equals x plus 2. And if I subtract x from both sides here, I get y equals negative x plus 6. So in this problem here, we have a slope of 1 over 1, rise, I don't know why I wrote a 2, slope of 1 over 1, so rise 1, run 1, and a y-intercept of 0, 2. So we'll find out which ones kind of give us that. And then on this one here, we have a slope of negative 1 over 1, fall 1, run 1, and a y-intercept of 0, 6. So the easy ones to probably look for are which ones have a y. Okay, I already see the answer. I'll hide myself here, but see the ones that have a slope, not a slope, a y-intercept of 0, 2 and 0, 6. I'm already seeing a 0, 2 and a 0, 6 on A. I don't see a 0, 2 or a 0, 6 on any of the other ones. I see a 0, 0, unreachable, a 0, 0, unreachable, a 0, negative 2, unreachable. It's got to be A. And to confirm that a little more so, because D doesn't matter, hello, I'm back. D doesn't matter here. Looks like that first one, 0, 2, rise 1, run 1, up 1 over 1, up 1 over 1. That seems to be working out. And then this one, fall 1, run 1, down 1 over 1, down 1 over 1, down 1 over 1. So it looks like A is that answer there. That is the one that gives me the graph. Look at how slope-intercept form really helped me, getting y by itself very simply. We could have found the x and y intercepts by doing the hide and divide method in standard form as well. But I liked looking at just the slope thing and playing with that too. Pretty simple answer there. Okay. All right, number 13. The graph of a system of linear equations is shown below. What is the solution of the system? I'm not going to spend a lot of time on this one. This is the point of intersection, 2, 4. That is the answer. So wherever they intersect is the solution. It looks like it's going to be C. That's it. And you know what? And that's it for the that's it for the linear systems of equations problems, solving those using the methods and stuff. I have 3 more problems to do. They are kind of other basic algebra, and I think one's on function stuff I'll show you. But if you're good at this point in the video, you've spent 50-ish minutes with me, 55 or so minutes with me. So I will let you go at that point. If you want to see a few more problems, go ahead and stick around with me for just a little bit longer. All right, number 14. Now I'm not going to spend a long time on these. 7x plus 9 equals 2x plus 9. Solve the equation, match the answer with it. Now, one thing you could do, if you have the answers here, is just substitute these and which one makes the left side equal the right side. But I'm going to do the algebra here and play with it. Subtract 2x from both sides, subtract 9 from both sides here. We're going to go ahead and get 5x equals 10. Divide by 5, you get x equals 2. Again, divide by 5, I should put x equals 2. That looks like it is C. That's it for number 14. Number 15, simplify the following expression. Notice there's no equal sign. We have x, y, and constants here, so we are going to get it down to a 3-term scenario with an x and a y and a constant. We are not solving anything. We are just simplifying it, breaking it down a little bit more. I'm going to rewrite these things so that the x's are next to each other, the y's are next to each other, and the constants are next to each other. One thing I want to stress, and I want you to pay close attention to, is the fact that I'm underlining, not that I'm color coding, but the fact that I'm underlining the sign that is in front of the variable as well, because that is the one that affects the variable. So I have 4x plus 2x for the x's. I have negative 7y minus 3y for the y's. And then I have negative 12 plus a negative 2, which is negative 12 minus 2, for the constants. When I combine like terms here, 4x plus 2x is 6x, negative 7y minus 3y is negative 10y, and negative 12 minus 2 is negative 14. So that is my simplified not solution. That is my simplified answer expression. So I think that's A. I want to make sure that the signs are all good. All the signs kind of change here. Oops, oh my gosh, look at that. That's a mistake. It is B, negative 10y. Got to be careful. I think that one is it right there. And finally, last problem, which mappings represent a function? Select all that apply. So there might be more or less here. If you don't remember, these mapping diagrams basically display your domain and range. In other words, your values for x mapping to your values for y. There are several ways you can look at these problems. One, just with the mapping diagrams, which is likely what I'm going to do. But I'll show you on A as well, something else that's kind of worth mentioning, is that these are kind of showing you coordinate pairs. If these are the x's and these are the y's, the arrows kind of point to what makes coordinate pairs here. So when 3 points to negative 1, that means there's a coordinate pair that is 3, negative 1. When 0 points to 0, there's a 0, 0. When negative 3 points to 0, there's a negative 3, 0. And when negative 6 points to 2, there's a negative 6, 2. So those are your 4 points. And what they're kind of asking is there ever a time where any one point is on top of another point? Meaning for any x, are there any 2 different y's? And that's an important question to ask. If I graph these, that would not be the case. There might be 2. The 0, 0 and negative 3, 0 are right next to each other in height, but none is right above another. This one seems to be a function right here. This one's good. Select all that apply. A and D is a function. Now, the way I'm going to use the mapping diagram to help me for the future ones is really just look at the arrows. There is a repeat of 0 on y in here, but it is used twice. Excuse me, there's no repeat of 0. There's a repeat of 0 here. It is not used twice right here. It is just one that the arrows point to. So if two arrows point to a single number, that means there's going to be a duplicate of y on here, which is allowed. What's not allowed is a duplicate of x in your coordinate pairs. And the way that you're going to see that is if there's a split arrow going from one single x value here. just because it's written here once doesn't mean it can't be used more than once. If I saw a 3 split over here as well as there, that's a problem. That's not a function. So I'm going to look to see any arrow splits. That's really all I'm looking for at this point. B, 2 has 1 point, 4 has 1 point, 8 has 1 point, 9 has 1 point. This is indeed a function. There's only one y for every x. That's good. C, negative 2 points to 1, 0 points to 1, 2 points to 1, 4 points to 1. This is indeed a function right here. It's not an issue. Now again, there's a duplicate on y, but that's allowed. There's not allowed to have a duplicate on x. Two y's for the same x. D is where you see this scenario that's kind of rearing its ugly head. Negative 2 pointing to negative 3 and a 5. That means there's a coordinate pair that's negative 2 comma negative 3 and negative 2 comma 5, which means when you graph those things, there's one that's like right here, one that's right here. That is not a function. It just needs to miss once for it to not be a function. While A, B, and C work, D does not. All right, so that's the last problem there, and that'll do it for me. This was a review on systems, solving linear systems using substitution, elimination, graphing, some word problems here and there. Some big talk. I know this was kind of a longer one here, but that ought to do it for me there. I hope this is beneficial for you. When we come to future videos, it will now be starting to write out word problems, graphing inequalities, and solving systems of inequalities, as well as solving word problems as we set up those word problems through systems as well. I hope you enjoy that one when we get to those. We'll probably start next week or so. So you won't hear from me for a little while unless I do a Q&A video. In other words, see you next time, but there might not be a next time for a while. My name is Mr. Robinson. Take care, guys.